Hello everyone. Let's talk about section 3.5, which is on equations of parallel and perpendicular lines. We're going to be spending some time talking about parallel and perpendicular lines again, but we're going to dig this a little bit further as well. So let's take a look at our learning objectives for today. So our major objectives are going to be to write algebraic equations for parallel and perpendicular lines, and we're going to use ratios to locate a point on a line that is both generally and precisely. So we are going to be doing a little bit of work right here. Let's see if we can take a look. So to begin with, we've got some definitions right here, but these are going to once again kind of up the ante a little bit. So let's take a look. For parallel lines, we had already talked about how parallel lines are going to be two lines that do not intersect. But I also want you to remember the old algebraic definition. Back when you were in algebra class, you also talked about parallel lines, but you talked about them in a very different way. Parallel lines were going to be two lines that had the same slope. So this is a great definition for parallel lines, but it is very, very different. If you want to draw the picture of both of these things, you can draw them at the exact same time. So these two lines that I've created right here do not intersect. They are, in fact, parallel to each other, but they also have the exact same slope. You will rise and you will run the same amount for both of these two lines. So this is a double trouble right here. We have two facts that we want to see if we can kind of marry. Same kind of thing for perpendicular lines. When we were talking about perpendicular lines a couple days ago, we had talked about how perpendicular lines were going to be two lines that intersected at a 90-degree angle. But also, back when you were in algebra last year, you guys had also talked about perpendicular lines, and we had talked about how perpendicular lines were going to be lines that have opposite reciprocal slopes. Once again, if you want to draw some of these things, you can draw them quickly and easily. So you're going to have one line that is going to look like this, and you're going to have another line that is going to come through and look like this. So the first line right here and the second line will form that 90-degree angle that we have, and so that is going to satisfy our geometry definition. But if you look at the slopes of the two lines, this line right here might have a slope value of maybe 2/1, and this line right here would then have a slope value of maybe -1/2. And so you can see that they're going to have opposite signs. One is positive and one is negative, and they're also going to have reciprocals. One is 2/1 and one is 1/2. If you're taking a look at an equation for these guys, you're going to probably find yourself faced with a slope-intercept form equation, which is going to be this one right here. Of the parts that we see right here, the part that we're most interested in is this one. M represents slope. And in fact, if you take a look at that last example that I had identified my slope using the M right there as well. B is another important fact, but that is not so important today because that is y-intercept. Being parallel or being perpendicular doesn't really mean too much about y-intercept. So we don't have to worry about that one very much. Let's take a look at a couple of examples that are really going to emphasize the power of that slope. So here's your first example right here that we're going to take a look at. It says find the slope of a line which passes through the point 6, -2 and is perpendicular to the line that is at y is equal to -3x plus 1. So if I want to draw this line right here, I can really quickly. So I would start off with my y-intercept at 1, which I've already drawn, and then I would use my slope, which is -3/1. And that would give me my good-looking line to draw from. So you got a couple of dots right there. You could also go up 3 units and over 1. And in general, you're just going to get a line that looks like this. Now, because our slope is -3/1, when we draw a line that is going to be perpendicular to it, we would want our line to look kind of like this. And the slope of that line, of the line perpendicular, is going to have a similar but slightly different slope. What was once negative will now be positive. What was once on top will now be on bottom. And what was once on bottom will now be on top. So this is going to be our new slope right here. It is positive, which means it is rising as you move from left to right. And it is going to be 1/3, which means it's going to be pretty shallow. It's not nearly as steep. And so this guy right here is going to match pretty nicely with my picture that I have right there. All right, here's a you try it problem that is going to be very similar to that. Pause the video and see if you can try that one out on your own. Parallel lines have the same slope, so once you are looking at the two different pieces right here, you are going to have the given line right there, and then your line is going to be right next to it. And one of the lines will have a slope of 2, and the other line will also have a slope of 2. Okay, so now we're kind of warmed up, and so we're going to try to use some of that in order to help us out in a couple of our upcoming steps. But let's also see if we can talk about our second objective as well. So we've already done some time talking about parallel and perpendicular. Let's see if we can talk about a ratio now. So what I have for you is I have a little bit of a story problem. I think the context of the story problem will help you understand the situation, so that's why I gave you the first problem as a story problem, which is not necessarily usually the case. So what I have right here is I've got a story problem about a sailboat race. If you've ever been in a sailboat race, they have usually triangular courses that they follow, and so this one is going to have the same kind of situation right here. And it says Captain Rob is racing his sailboat against his arch rival Sailor Greg, and they're going to be racing around a triangular course. Captain Rob has rounded the corner at buoy C, which is right over here, and he is going to be approaching buoy D. So that means he's going to be flowing around like this, down here towards buoy D. Captain Rob is located at point F, which is on CD. So he's somewhere along this portion of the course right here. And this point F is going to be located such that the distance from C to F and the distance from F to D is in a ratio of 3 to 5. And so what we want to do is we want to see if we can find the location of this point F. It's going to live somewhere along the line. And since the ratio is not evenly split, 3 to 3 or 5 to 5 or 1 to 1, that means that our point F is not going to be smack dab in the middle of C and D. It's going to be closer to one side than it is to the other. Specifically, since the smaller number is first, it's going to be that means that CF, the distance from C to F, is going to be shorter. The bigger number is second, which means the distance from F to D is going to be longer. So we need to see if we can figure out what that distance is. What I have for you right here is I've got a nice 6-step process that will walk you all the way through it, and it works out really nicely each time. And so if you can follow these steps and kind of internalize them, then you'll be in great shape. My job today is to show you exactly why these are the 6 steps, and so that you don't forget them and they don't just seem like they're just randomly being assigned to you. So one of the first things we need to do is we're going to do a little bit of a strange step right here. And this first step says add the ratio values to find the ratio total. So our ratio was 3 to 5. And so if you take a look, I have my first step done right here. I'm going to take my 3 and my 5 and I'm going to add them together to give me 8. What this is going to do is this is going to tell you that the distance all the way from point C to point D is going to be split into 8 equivalent chunks. And if you take a look, I've done that splitting right here. 1, 2, 3, 4, 5, 6, 7, 8. And I've tried to do my very best to split them so that they're all evenly spaced in the same size. Okay, so now what we're going to do, step 2, is to choose our favorite point. So we have a couple of points that we're going to be looking at, point C and point D, and we're going to find point F somewhere in the middle right there. So we're going to choose whether we like C first or D first, and it's your personal pick. I personally would choose point C. And one of the reasons why I would choose point C is because it's the first one, and the other reason is it's the one that's furthest to the left. We're going to have to move towards point D, towards the right, just like you would do when you're writing a sentence or writing down numbers, in order to get to that point F. And so that's the choice that I'm going to make every time. And that's because I'm boring. Not because you have to, but because I'm boring like that. And sometimes boring is good because it's predictable. And so I'm going to choose point C right there, -4 or 5. All right, now, let's see if we can do a little bit of an estimation here. So now, remember that our ratio was 3 to 5. Now, I've already laid out my tick marks right here. And so if I start at point C, which was my favorite point right here, watch what's going to happen. If I jump out 1, 2, 3 spots, I'm going to end up right here. Now, the other part of that ratio was the number 5, if you remember. Now, take a look. If I start at D here and I jump back 1, 2, 3, 4, 5, I'm going to end up at the exact same spot right here. That's why it was important that we add the 3 and the 5 together to get the 8, so that there's space for the 3 on one side and there's space for the 5 on the other side. And I have space for both, so I'm good to go. If you take a look, once again, this is also going to verify what I had mentioned earlier. The distance from C to F should be shorter, and the distance from F to D should be longer. Now, I haven't done a great job of marking these tick marks off, so I have a bit of a ballpark idea about where I want my answer to be, but I am certainly not confident. I can't say beyond a reasonable doubt that my location right here is absolutely perfect, so I am going to need to do the work. But this is going to give me an idea about where I'm expecting to find my answer. It looks like I'm going to get a very small positive X value and a pretty small Y value, but a little bit bigger. Everything's going to be positive, though. Let's find out. So now, step 3, calculate the slope. So slope is something we've been talking about today. We're going to keep on talking about it. We want to find the slope of the line CD. And one of the interesting things about this is we are not going to reduce this slope at all. It is not going to be reduced. So let's calculate the slope. You can calculate it by bunny hopping your way across your drawing, or you can calculate it by doing the actual calculations. I'm going to do the calculations because I'm a math teacher, but you don't have to do them if you don't want to. So my calculations are going to start with the y values, and I'm going to do -3 minus 5. This line is going down, so I'm expecting negative numbers. I'm going to also do 8 minus a -4. There you go. And when I do some calculating here, I'm going to get a -8 in the top. And then I'm going to get an addition problem down here. And as tempting as it may be to reduce that fraction, we are not going to do that. And that's important because this is the actual pure slope of this line, and it's going to be long. We want to know the full distance that we need to travel down from C and the full distance we need to travel over from C to get to point D. We don't want to have any stops that are going to show up in the middle. So we want the full distance right there, -8 and 12. Okay, next, step number 4 is a critical step right here. So now what we want to do is we want to take this rise value that we have right here and this run value that we have right here, and we want to shorten it. Because remember that we're not actually supposed to be traveling from C all the way to D. We're supposed to be traveling to point F. So we need to shorten this down. And so the way that we're going to do that is we're going to take our rise value, which was -8, and we're going to take our run value, which was 12, and we're going to multiply them by our ratio. Now, when we're multiplying by our ratio, this is the trick. This is the thing that people mess up. The ratio was originally 3 to 5, and what we're going to do is we're going to use the 3, but we're also going to use that total number that we had come up with as well. We're going to use the 8. So the 5 is not directly written down. We did use the 5 to create the 8 right here, but we're not actually writing down the 5. That's a trick that a lot of people struggle with. They see 3 to 5, they want to write down 3 to 5, and they want to use 3 to 5, and that's just not the case. And so we're going to use 3 over 8. The reason why we're choosing 3 is because, once again, we had chosen C to be our favorite point. C was the first point, so we used the first number. If up here in step number 2 we had chosen point D, then we would have picked 5 to be our numerator, and we would put a 5 here and a 5 here. So you can use the 5 if you'd like, but you just don't use the 3 and the 5 at the same time. You're going to use 3 over 8, or you're going to use 5 over 8, and that is based off of whether you pick C or you pick D in step number 2. All right, let's see what we calculate. So when we're going to calculate these ones, this first one cancels out really nicely. The 8s are going to go away, and we're going to end up with -3. All right, now for the second one right here, you're going to get 12 times 3 over 8. You can reduce first, and then you can multiply by 3, or what you can do is you can multiply by 3 first, and then you can reduce. It really doesn't matter. What you're going to end up with is you're going to end up with 9 over 2, or 4.5. Now these are the numbers, this is the distances that we need to travel to get from point C down here to point F. And so what we're going to do is we're going to remember that when we're doing these travels, that this -3 right here is actually the rise amount. You want to rise -3. So if you're starting here at point C, you want to come down 3 units, and then you're going to want to run 4.5. So you're going to come down 3 units, and then you're going to come over 4.5 units, and that will get you to the point F. And that looks like it's getting us right into the ballpark. Now, if you want to know the exact location of point F, I recommend that you don't actually rise and run on the drawing, but rather I would actually ask that you actually just do a little addition or subtraction. So this is going to be step number 5. Let's do some adding and subtracting. So our original point C was -4, 5. That was the point that we had in step number 2, -4, 5. And what I'm going to do is I'm just going to simply use my rise and run values, and I'm going to just tag them on here. So remember, rise is the vertical piece, and so I'm going to stick that with the 5. And run is the horizontal piece, so I'm going to stick that with the X. So I'm doing the same things. I'm going to come down 3, and I'm going to come down 3 by doing 5 minus 3, which is going to take me down to 2. And then I'm going to travel over to the right, 4.5, and I'm going to do that by doing this piece of addition right here. And when you do that, this is going to give you your answer, which is step number 6. It turns out that point F lives at the point 0.5, 2. If you look at my drawing, 0.5 units over, 2 units up, yep, looks pretty great. I'm feeling confident. My drawing is going to back up my calculations, and my calculations are going to confirm what my drawing created. So I'm feeling confident, and I don't have to worry that maybe I did it right or maybe I didn't do it right, because everything looks like it's matching very nicely. So I like that a lot. Okay, here's the second thing that I'd like to do today. And our second piece that I'd like to do is I'd like to take this idea that we're working on here with our parallel and perpendicular lines and our slopes, and I'd like to use it to write some proofs, some nice simple proofs about some shapes. So what I have right here is I've got a collection of points which I'm going to call M-A-T-H. Each point has its own ordered pair. And I'm going to take those ordered pairs and I'm going to plot them. So I've got my M-A-T-H piece right there. Now, if you look at that figure, I bet you have a pretty good idea about what the name you would give it. Would you call it a square or a rectangle? Would you call it a quadrilateral, trapezoid, polygon, pentagon, octagon? I'm sure you have a pretty good idea in your mind as to what you want to call it. But what we want to do is we don't just want to say it out loud or think that we know, we want to prove it. And so once again, for proofs, you want to make sure you're going slow and you want to take those baby steps. You're not going to make any big jumps. You're not going to say, well, it's a rectangle because I say so, because that's a really, really big jump. We're going to go slowly and we're going to try to make our choices. And also, our goal is already going to be set out for us. We want to show that this is actually a parallelogram. So, here's the process that we're going to use. We are given a set of 4 points, and what we're going to do with those 4 points is we're going to collect some info. Now, the info that we've been talking about so far today has definitely been slope. And I want you to calculate a lot of slopes when you're doing these proof problems because they're going to help you out. And the way that they're going to help you out is they're going to help you find any of those parallel or perpendicular lines because they're going to show up in certain ways, and you're going to be able to use that to your advantage. There are other things that you can do with ordered pairs as well, and so I wanted to remind you of this, not because you need it for this problem, but because you might need it in the future. Distance formula works for points, the midpoint formula works for points. Anytime you have ordered pairs, you have lots of formulas that you can use. Slope isn't just the only one, but it's a really good one, and it's the main one we're going to focus on today. Especially since we're looking at parallelograms. For parallelograms, the main thing that is going to define a parallelogram is that it's going to have 2 sets of parallel lines. So let's calculate some slopes. We're going to need 4 slopes, 1 for each side, and fingers crossed, we should end up with 2 matching sets. So I'm going to calculate 4 different slopes right here. I'm going to start off with the slope of MA, which is my very first line, running right here. And I'm going to calculate the slope of this. And I'm going to use my ordered pairs that I have right up here. That's going to be 5 minus 2 over negative 2 minus a negative 5. And when you're calculating the slope for MA right here, it turns out pretty nice. We're going to get 3 in the numerator. And this is going to turn into an addition problem. And you are going to end up with 3 down here as well. It's going to be a positive slope of 1. Then my second slope that I'm going to do is I'm going to do AT. AT is my second line, and so I'm just being boring and going around in the same order. For AT, I have my 2 points right here, and I'm going to calculate slope. That's going to be negative 1 minus 5 on top, and that is going to be 4 minus a negative 2 on bottom. When we calculate the slope for this one, it is negative. We're going to end up with a negative 6 on top and a positive 6 on bottom. This is going to reduce down to negative 1. Now, these slopes don't match, so that's a bit of a bummer, but maybe if I keep going, I'll find some matches. So my next line that I want to do is TH. I want you to notice that I'm labeling my work. I think it's important to label my work, and I'm also showing my calculations here, and I think that that's important as well. T is up here, and H is down here, so it's going to be negative 4 minus a negative 1, and that is also going to be 1 minus 4. So now this one's an interesting one. In the numerator, we're going to end up with negative 3. And in the denominator, we're going to end up with negative 3. A negative divided by negative is a positive. And we end up with 1. My last slope that I'm going to calculate is going to be the wrap-up one. And it's going to go from H all the way up here to M. So that means I'm going to be using this point H right here and this point M right there. So let's see if we can do it. That's going to be 2 minus a negative 4. And it's also going to be negative 5 minus 1. Calculating the slope for this one, we're going to end up with a big 6 in the numerator and a negative 6 in the denominator. We're going to end up with a slope of negative 1. Okay, so now if you take a close look at what we've created right here, we have matching slopes here. And then we also have matching slopes here. Excellent. That's exactly what we needed to have happen. Parallelograms are supposed to have 2 sets of parallel lines. We are going to have our 2 sets of parallel lines. They are going to show up on on the top and on the bottom, on the left side and on the right side, which is going to be fantastic. Now all we really need to do is just organize this into a proof that somebody could read through carefully and easily and get the information from without actually even having to look at the drawing or do the work themselves. So let's do it. As usual, your proof is going to start with your given information, and the only information we started with was these ordered pairs. So I've got my list of ordered pairs and I've got the term given already put in there. Okay, so now step number 2, this is where you're going to collect that information, and we already did the work for it, so what we're going to do is we are going to talk about slopes. Alright, so we have my label right here, slopes of, and so we're going to say slopes of, and I'm going to just make a big list of all the slopes that I calculated one at a time. So I'm going to say slope of MA, M is equal to 1, and then I'm going to do AT, M is equal to -1. I'm going to do TH, M is equal to 1, and I'm also going to do HM, M is equal to -1. Now this looks really nice. You can see how it's very organized. Okay, so what was the technique that we used? What's our reason for this? And basically this is just the slope formula, or the definition of slope. So there you go. We're just using the normal formula right there. Okay, so now what does this mean to us? This is where step number 3 is going to come in and kind of break it down. Remember, we're interested in a parallelogram, so this word parallel's got to show up at some point. And so now what we get to do is we get to make some statements about this. So these two guys have matching slopes, and so we get to make a statement about that. I am going to state that MA is parallel to TH. And the reason for that is because they have those matching slopes. I also get to make the same kind of statement for AT and HM. So now I have my 2 sets of parallel lines. And this right here, this is based off of what we learned about today. So if we go back and we look at our very first page, we saw that parallel had 2 different definitions. The one that I'm working off is this one right here. Parallel lines have the same slope. That's the algebraic definition of a parallel line. So I'm going to say definition of parallel. And I'm also going to state that I'm looking at the algebraic one, because I think it's important to notify or to distinguish between them. All right, so great. Now we have the fact that we've got these parallel lines, which is going to be fantastic and wonderful. And so now we're going to bump it up a little bit more. Step number 4 right here. Because we have these 2 sets of parallel lines, we get to finish this guy off. We are going to state that MATH is a parallelogram. And the main reason that it is a parallelogram right here is because of the definition of parallelogram. Parallelograms are defined as having 2 sets of parallel lines, and we have those. So this is going to be by definition. And this is going to be parallelogram. Great. Okay, there are 2 you try it problems, and I'd like you to try those out. One is a proof right here, and it's going to be a proof about right triangles. I want you to think about what it means to be right while you're working on your proof right there. And then our second problem that we have is going to be a problem on another ratio. And so we've got a line segment AB, and we have a ratio of 4 to 1, and we want to see if we can figure out where the point P is going to be located on that line segment. Pause the video now and see if you can try those guys out. Here's our answer for you try it problem number 5. What we have right here is we've got our work for our slopes. Once again, we're dealing with a right angle, which is 90 degrees, so we're looking for perpendicular slopes. First slope, we really didn't need to do. If you look at the picture, you're going to know the GA is not part of that 90-degree angle, so if you didn't do that part, you don't need to. These second 2 slopes are going to be connected to each other. They certainly don't match, but they are opposite reciprocals. One is positive, one is negative. One is 2 over 1, and one is 1 over 2. So when I state my given statement, I'm going to put my ordered pairs. Then I'm going to state off my slopes that I need, and I'm not going to use that top one because I don't really need it. I'm using the definition of slope for that. Then I'm going to make my statement about my perpendicular lines based off of the algebraic definition of perpendicular lines. And then lastly, I'm going to make my statement that angle GAK is a right triangle, and it is by the definition of a right triangle. Do your last you try problem right now as well. when you are working on this guy right here, what you're going to find is that you have 5 tick marks. There are 5 spaces that we're going to use and 4 tick marks, splitting them up. I'm boring once again, and I picked point A because it is the one furthest to the left, and it's the first one. Then I calculated my slope, and I didn't reduce it. I used my value that showed up first in my ratio, 4, because I picked the first point, and I used my total, so I used 5, 4 over 5. I took my rise and run values for my slope, and I multiplied them both by 4 over 5. That gave me 2 ugly fractions, and I used those 2 ugly fractions to come up with these decimals. I needed to go 6.6 units over and 3.8 units up. Looking at the drawing confirms, and it makes it look exactly the way that it's supposed to. Okay, great job. Now it is time to move on to see if you can do the 3-5 practice problems. Thank you.